Good morning, everyone. You might have noticed I did not get your lecture posted until yesterday. I posted it once and then it on my YouTube channel. And when I got up the next morning, because I set it at night, when that's the least internet traffic anyways for around here, when I got up next morning, it had failed. So I had to put it back up yesterday, and it actually took like 2 hours. It's there now. In fact, the one for your class as well as the one for the night class are both up, and I've given you links to both of them. You can probably like look at it when you see it's the same problem that we solved in your class, unless I made a mistake on there or you didn't understand it, then you can just skip over that one. If I had made a mistake on it in your class, then you might want to look at it, because chances are I didn't make a mistake in the second one. But also that other one had some more examples that you didn't get, because your class is only 50 minutes long. So it's certainly useful for you to at least watch for the extra examples. Like I said, just skim through, fly through it or whatever, till you get to a drawing that doesn't look like an example you had. So does anyone have any questions before we get started? I also set the homework dates, and remember your test is due tonight, so don't forget that if you hadn't already done it. So make sure you get that done. And I think I have a couple homeworks, or at least one homework due tonight. And then of course the chapter 5 concept questions will be done due Sunday. And then the chapter 5 homework will be done Wednesday. So make sure y'all get that done. It looks like we don't have any questions, so I guess I'll just get on started to teaching some more of chapter 5 stuff. So first thing I want to do is I want to solve a problem where I'm going to design a banked curve so that you can actually make a turn with it without friction. Okay, so that's one of the things we can do now that we've been introduced to friction, as well as normal force, as well as centripetal acceleration, because obviously if you're going to turn, you've got to have the ability to accelerate towards the center of the turn, or else you're not turning. So let's get started, assuming again still no one has any other questions. I'm going to turn on my document cam and try to explain what I'm doing step by step. Okay, so what we're going to do is we're going to imagine a curve that's banked at some angle theta. Okay, again, I like working with symbols, because when you work with symbols, you get an answer that works in all scenarios. But you should always go ahead, if you want to, if you're not comfortable with that, go ahead and replace the symbols with some numbers and work the example again. That's certainly fine. But like I said, by doing it in symbols, it teaches you stuff that, one, it teaches you an equation that you can use for all cases, but two, it also teaches you how this angle theta, say, depends on the coefficient of friction, or how it depends on the mass of the car, all that kind of stuff. So what we're going to imagine is there's a car on this incline. Okay, and it's traveling at a velocity v, say. So, and that's coming out of the screen, of course. V is its velocity out of the page. What I want to do is make a free body diagram so I can make some sense out of exactly what's going to happen with this problem. So I'm going to draw the car as if it's a point object. I'm sort of tempted to draw a tilted axis, but it's going to turn out that that's not really that helpful, so I'm not going to do that. But there's the car. We can assume its mass is m, say. Okay, and we're going to say no friction. So without friction, what that means is basically you should be able to make it around this curve if it's banked properly, long as you go the appropriate speed, even if it's icy. Okay, so if it's iced over, you should be able to still go at the proper speed. But if you go too fast, of course, you're going to sling off the end. If you go too slow, you're going to slide down and hit the guardrail on the inside, if there is a guardrail. So the forces acting on it, of course, are, I'm going to draw a line to represent the incline angle, and just remind everybody that that angle is theta. So acting at an angle perpendicular to the incline is this normal force. Okay. Also acting on the vehicle is a weight W. And that W is going to be equal to M times G. I should have wrote it over here, but I didn't because I'm a goober. So anyways, not that big a deal. I'm going to make my y-axis this way. I'm going to make my x-axis that way. And then, of course, you have that. So what I realize now is that I have a component of force in the positive x direction and a component of the normal force in the positive y direction. So I wrote them in red for some ungodly reason. Okay, so two other people just came in. Hold on a second. All right. So if this angle is theta, you can see that this is 90 minus theta. This would be theta as well. But since this and this is perpendicular, this is 90 minus theta. So this angle up here must be theta. So this right here is Fn times the cosine theta. And this here is Fn times the sine of theta. Okay. So now I'm going to write the summation of forces in the y direction. Is equal to mass times acceleration in the y direction. But the y direction is up and down like that. We do not really expect any the vehicle to jump off the thing that way. So this acceleration is again going to be 0. So what I get is Fn cosine theta minus mg is equal to 0. So that means the normal force has to equal mg over the cosine of theta. So there's another instance in which the normal force is not the weight. Okay. Now, if we were dealing with friction, that would be a very important thing to consider. I want to find the angle theta really is my most important issue, and I'm ignoring friction. So what I know is that the summation of forces in the x direction have to give me the appropriate acceleration to make a circle. So I'm going to assume the circle has a radius r. So turn has a radius r. And of course, the car is going at a velocity v. So now I write the summation of forces in the x direction equals mass times just plain acceleration, because again, that's the only acceleration we're dealing with. So when I do this, I see that Fn times the sine of theta is the only force supplying a centripetal force. And that has to be equal to the mass of the car times v squared over r, because that's our centripetal acceleration. Okay. So now I can combine, let's call this equation 2. Call this equation 1. Combine, well, equations 1 and 2. And what we'll get is, notice Fn, I'm just going to replace it. So I have a mg over cosine theta times the sine of theta is equal to mv squared over r. You can see the m's cancel out, which is good because we'd hate to have a different curve for each vehicle that rode on the road. So you'd have like a different angle for a Mack truck than you'd have for a Prius, or even for two different Mack trucks. So that would be a problem. We can see that sine over cosine means something. Anybody recall what sine over cosine is?
Tangent.
Yep. So we write tangent theta is equal to v squared over gr R theta equals the tangent inverse of V squared over GR. And that's how you bank a curve. Now, again, this is for exactly that speed V. And you're assuming zero friction. So, but in the case of really zero friction, that will work if you have even a little bit of friction all the time. So that angle is really still a good banking angle. But the deal is, if it's an icy situation, then your friction goes essentially to zero. At that time, it actually can become a little bit of a hazard, because if you're going too slow, which is probably the normal thing to do when there's ice on the road, if you're going less than 25 miles per hour on a curve that's banked for 25 miles per hour, and you actually have it iced over, then you're going to have no friction or very close to no friction, and the car might actually slide down the incline, which in some cases is a ravine followed by a wastewater retention pond, or sometimes it's a guardrail or stuff like that. Also, if you, of course, go faster than the design angle speed, then the friction again will be insufficient and you'll slide up the incline. Okay. So that's the way you go about designing a curve. Again, if you want to look at adding numbers in there, you can see that I actually did a design of a bank curve, and I actually computed it with some numbers to see. So let's try just a quick example and say, if V is equal to 60 miles per hour and R is equal to, let's say, 50 meters. Then what is theta? Okay, so this is sort of a follow-up example, but we're just applying the results is really all we're trying to do. And of course, we want to find out, does anybody recall what 60 miles per hour is in meters per second? Anybody recall? I will double check just to make sure, but it should be 26.8. Now I'm double checking just to make sure, and someone else has come into the classroom. So I'll do
26.8.
It is 26.8. Thank you. And that's meters per second. And I'm going to assume this actually had one decimal place, so we all have 3 sig figs and life will be nice. Okay. So with this, I'm then going to say, okay, well, theta is equal to the inverse tangent of, in this case, I'm going to have 26.8 meters per second squared over 9.80 meters per second. Notice this will be up by a meter because it's meters squared per second squared, and this is just meters per second squared. So we have an extra unit so far of meter in the numerator, which is where we put in the 50, and that takes care of it. So you can see ultimately there's no units here, which is what you expect for the argument of an inverse tangent. So now I'm going to take inverse tangent. So trig function inverse tan of 26.8 squared. And then I'm going to divide that by parentheses 9.8 times 50. And in case you're wondering, you end up getting 55.69 degrees. And technically that's 697 degrees. So using 3 sig figs, these two are extra digits, and you should really just call it 55.7 degrees. So if you look at that, that's actually pretty steep bank. Remember, the blue lines should be horizontal on my paper. So this is horizontal right here. 56 degrees is essentially that angle. So that's how steep the curve would be for 60 mile per hour at a 50-meter curve. Now, a much more general or normal curve might be 100 miles, 100 meters in radius. So that would obviously cut down the angle quite a bit. But you can see that's a pretty steep angle. That's where you're starting to get uncomfortable climbing it if it were, for instance, a roof, where the little bits of gravel are falling off as you're walking on it. So that's an instance of a calculation using the formula we just derived. And if that equation is numbered in your book, you can use it, but I don't recall it being numbered. I will double check real quick just to make sure. Yeah, they got the same thing I did. They did example 515. And yeah, they did not number that. So they are sort of expecting you to derive that whenever you're given such a problem. Okay. Now what we're going to try to do is do one in which there is friction. And this is a much more complicated scenario. Actually, no, since I've shown you this, I want to make sure we finish chapter 5 this week. And really, I gave you a little hint about that, using that swing issue where the poor folks got tragically injured of the Golden Gate Bridge. That was sort of a pseudo example of using mv squared over r. I'd really like to do a more robust example, because those are the two major new topics: is friction, which I've done quite a bit now, and mv squared over r, which I've done here again. But what I want to do now is another one where you're talking about something traveling, say, in a circle, whether it be vertical or whatever. So let's try another example. This one was example 1. This was example 2. And I'm just calling it that. I mean, we're not referring to it in any particular way, so I don't even know why I take the time to do it. But here's example 3, just to continue with our process. That might help us a little later when you're talking to other students about a particular problem you had a problem with, or when you're talking to me about a problem you had a problem with. So let's consider a scenario where we're going to actually use the mv squared over r to figure out something. So let's say, for instance, you're swinging a bucket of water vertically with a radius r, okay, and a velocity v. Okay, that's supposed to be perpendicular to the r. What I would like to do is figure out how fast it has to go must the bucket move to keep from emptying. So if you actually take a bucket and just, with no speed whatsoever, just turn it upside down over your head, obviously what would happen when the bucket gets right here, it's just going to pour water on your head. But you've probably done this before on your own. You can swing that bucket. If you swing it fast enough, then the water will stay in the bucket. So we're going to try to calculate that. And the way we're going to calculate it is this. We're going to draw a free body diagram of the bucket upside down. Okay, so here's the bucket upside down. What we have acting on it is a force in the downward direction that's equal to the mass of the bucket. That's the bucket in the water, by the way. It's equal to the mass of the bucket times g. And then we also have, let's say, tension force supplied by our arm or by a rope or whatever. I'm just going to call it a F. Okay. And that's the force that I actually have to exert on it to keep it going in a circle. In other words, if I let go of it right there at the top of the circle, it's just going to take off and go this way. But I have to supply that force going inward. Okay. Now, the summation, we'll call this the positive y-axis. So the summation forces in the y direction equals mass times acceleration in the y direction. When we go to solve this problem, up is positive, so I get negative F minus mg has got to equal mv squared over r. Okay. From that, you can see that the f would actually equal mv squared over r negative plus mg.
I can't quite read the formulas there.
Okay, I'm writing too small, I guess. Let me pull them up closer to you real quick. Were you able to get the ones on the previous example?
The previous example I followed through, yeah, I followed along with.
Okay.
And where are we getting the mv squared over r from?
Remember the acceleration that we derived last class to maintain a circle is called the centripetal acceleration. And to actually travel in a circle, you have to supply v squared over r acceleration. So the right-hand side is mass times the acceleration required to keep it in a circle. Hence, I put in v squared over r for a.
Okay. So centripetal acceleration v squared over r, and you're just replacing ma. Gotcha. Okay, thank you.
No problem. Now I got to check my math here because this may or may not have the double negatives were a pain in the butt. And actually, the v squared over r should be a negative as well. So that's what's going on. This should have been a negative because notice the acceleration has to be in the negative y direction, it has to be downward. So all these forces are acting in the same direction. So let me kill this real quick. Does everybody understand why I said the mv squared over r has to be negative? Anybody not understand why that has to be negative? Okay. So
well, the
F,
acceleration is pointing towards the center of the circle, right?
exactly, and we call it up the positive direction.
Okay.
So F plus mg is actually equal to mv squared over r is the way we can write it now that I got rid of all those negatives because there's a common negative to everything. So now I can say that the force is actually going to be mv squared over r minus the weight, because the weight's going to be helping your arm try to pull it in a circle. So the minimum velocity that can go is the velocity that occurs when you have to apply no force whatsoever. So the minimum required velocity to prevent spilling is the velocity when F goes to 0. Okay, so the minimum required velocity is to prevent spilling is the velocity when F goes to 0. So what that means is as F goes to 0, then mv squared over r goes to mg, which means that v, notice the m's cancel out again, so it doesn't matter how much weight it is. So v is going to be the square root of r times g. So as long as you're going a velocity equal to r times g raised to the 1/2 power, which notice this is meters per second every second times meters, so that's meters squared per second squared. Square root of that gives you meters per second. So that's all you need. So if your arm, let's say your arm is, let's say, what, 60 centimeters? If arm is about 60.0 centimeters, then V would equal the square root of 0.600 meters times 9.80 meters per second every second. Square root of that gives me 2.4248 meters per second. That should only have 3 sig figs, but it was a 4 there. So I wanted to make sure when I rounded that to a 5, if I would round that to a 5, you would think it's supposed to round this up. So I just didn't want to do that. So I left it as 2.4248. So you realize in later calculations, you should use, if you had to use it, you'd use 2.425, but you should still round it to 2.42. Okay. So there's another example of what it is. And the 2.42 meters per second is really not that fast. In fact, if you wanted to convert it to miles per hour, for instance, I can do that really quickly. I'll say 2.42 meters per second is equal to 5.41 miles per hour. So 5.41 miles per hour is all you need to really do to spin that bucket, to keep a bucket of water or a bucket of sand or whatever from spilling. Now, another neat part is you might say, well, what force do I have to hold it with if it's going that velocity? So this was example 4. What force would I have to apply at the bottom? So example 5. Okay. So in that case, we got another free body diagram, which we're just basically going to draw like this. There's the mass. We still got mg pointing down. And now we have a force pointing up. That's F. And of course, we know that the acceleration is upward as well. And that acceleration is equal to V squared over R. Okay. So Newton's second law on this one gives us F minus mg is equal to mv squared over R. And we know what V is. V is the square root of RG. So we'll say F minus mg is equal to m times R times G over R. So now you can see the R's cancel out. And that's because, remember, V was the square root of RG. So that just V squared just becomes RG. And then, of course, over that. Now that you have that, you can see that F is actually equal to 2mg. So if you're using, for instance, a 10-pound bucket of water, then yeah, it would be weightless at the top. So water wouldn't pour out, but then it'll be double the weight at the bottom. So you have to be holding up to 20 pounds to keep it in the circle at that point. Does that make sense? All right. So I want to, has everybody got all that? I don't know if there was any pixelation going on. I thought the image was pretty clear, but and I know that's not in focus, but I imagine it's big enough that you can still read it, even though it's not that great in focus. Anybody need to see any other parts of that? Okay. Let's go on to the next part. So now what I want to talk to you about is uniform circular motion really just means an object going in a circle, which is obviously means constant radius, but it also means at a constant speed. So that's what uniform circular motion is. But in fact, in reality, there's a lot of ways you can go in a circle that isn't necessarily uniform. So for instance, if you're taking a curve, and actually there's some reason to do this if you ever take a advanced driving course or something like that. Sometimes people will teach you that there's, depending on whether your car is front wheel drive, rear wheel drive, what its weight distribution is and stuff like that. Sometimes if you go to take a turn, it's actually better to speed up a little bit in it. And that the reason that happens is basically it puts more weight on the rear end of the car and actually allows it to sort of tilts with the turn in some sense. So weird stuff like that can happen. But if you did that, if you're actually in the middle of the curve, then you're speeding up and therefore you're accelerating in the tangential direction. So what I want to do is show you how we have to deal with that motion. And it's really nothing necessarily that big of a deal or nothing new. We actually ran into it before when I mentioned tangential acceleration and our first day. But let me tell you, the generalization of what we had is that the acceleration has to be equal to A tangential plus A centripetal. Okay, well, that looks bad. A little better. So this is tangential acceleration. And that means speedometer is changing. So in normal circular motion, you would just say your cruise control on 30, and that, of course, cruise control is not perfect, but we'll pretend like it's perfect for this. You set your cruise control and say 35 miles per hour or 40 miles per hour, whatever you want, and then you just drive in hopefully a really big open parking lot by turning the wheels, say as far as you can, and then just riding in that circle. Now, obviously, you don't want to try that at 40 miles per hour and turn it as sharp as you can. That could lead to some problems. But as an example, that's what you could consider. And as long as you're staying at 40 miles per hour, then that term is 0. The other term, on the other hand, is the one that we learned, and that's AC has a magnitude equal to V squared over R, which we also learned was omega squared R. So that comes in handy too sometimes when you know omega, which is the angular frequency or the angular speed, and it's 2 pi over the period of the rotation. So just keep that in mind. So that's how you deal with non-uniform acceleration. Your book does an example, and I think that's plenty straightforward for you to figure out. So I'll leave that to you. I just wanted to make sure I covered the topic. Now, the other thing that I wanted to do, I think, yeah, let's try another rotation problem. So I'm going to now do something where something's rotating but not vertically. So this will be example 6. And what we're going to imagine is a string in someone's hand and a mass on the end of that string, and that's an angle theta. And why I wrote it so small, I have no idea. So we'll say the angle right here is theta, okay? The ball has a mass m, and in fact, it will be following a circular path like this, whose radius is r. Okay. I'm going to assume it's traveling at a constant velocity v, which is obviously perpendicular to the path, and the radius is r, and I want to calculate what theta is. Okay. So this is, again, not unlike the fuzzy dice problem, where we're going to have something tilted at some angle and we're going to have to solve it. So let's draw our free body diagram. Our free body diagram is going to be this. I'm going to call that the positive x-axis. I'm going to call this the positive y-axis. Okay. The forces acting on this are, of course, the weight of the ball, which is W equals mg. And then you have a tension in the rope, T. And in fact, this angle right here is theta, which means, notice this is sort of like a railroad track, this and this, they're parallel. And then you got a bar across it. And whenever you have a bar across it, all the angles are equal. So this angle and this angle are interior angles. It's between the railroad tracks, and they're on alternate sides of the rebar. So this angle has to be theta as well. Okay. The reason I do that is because I need to make the components of T in our axes. So you can see this angle here is theta, so this must be T sine theta. And this angle again is theta here, so this one must be T cosine theta. Okay. So that tells us Newton's first law, or second law, is summation of forces in the x direction equals mass times acceleration in the x direction. And that really is the only acceleration. So I'm just going to call it A for right now. And what that's going to give us is T cosine theta is equal to, now it's got to spin in this circle, so it needs a radial acceleration called the centripetal acceleration. So it'll be mv squared over r. That's why I gave you the v and the r and the m there. Okay. You'll find out you won't even need the m, but here we are. So now I take the summation of forces in the y direction equals mass times acceleration in the y direction. Again, we're assuming we're at equilibrium where this angle has settled itself, so there should be no more acceleration in the y direction, so that's going to be equal to 0. In this case, I just get T sine theta minus mg is equal to 0. So I've got T sine theta is equal to mg. That's going to be equation 2. That's going to be equation 1. What I'm going to do, and this is that trick, I think this class ended up not showing it, the trick to them, but now I'm showing it to you. One way you can deal with two unknowns, notice we have an unknown tension and we have an unknown theta. You have to have two equations, but one of the ways you often did not learn in your math class, you learned ways, multiply one of the equations by a negative number and the other equation by some positive number, and then you can make two terms cancel out, or you can solve one of the equations for one of the variables and then plug it in the other equation, all sorts of stuff like that. In this case, I'm actually going to divide them. So I'm going to say take 2 divided by 1. And when I do that, I get T sine theta over T cosine theta is equal to mg over mv squared over r. You can see immediately that the t's cancel out and that the m's cancel out. And you're going to get sine theta over cosine theta is tangent theta. And tangent theta is going to equal gr over v squared. So we can already see that theta will equal the inverse tangent of gr over v squared. So let's say the velocity, so we'll call this example 7. If v equals 2.42 meters per second, notice that's the same speed we had before. And let's say in this case, let's say, yeah, this is a pretty decent length ruler. You can see it goes right across here. It's about the length of the diagonal of 8.5 by 11 page of paper. So we'll say 30 centimeters is a good R. And R equals 30.0 centimeters. Then what would theta be? Okay, so there's a new question. Easy peasy. We've already got the equation. I can just say theta is equal to the tangent inverse of 9.80 meters per second every second times 0.300 meters over 2.42 meters per second squared. I'll change this to a square bracket. And then I'm going to get 9.8 So I got the square, or excuse me, the inverse tangent of 0.502. And that gives me 26.6 degrees. Again, it should be 3 sig figs, but again, because it ended up on that 5, I wrote extras. Okay, that's a pretty big sag, right? So that 2.42 meters per second is really not that fast. You've probably spun a rock over your head before on the end of a rope or something like that, or a ball or anything like that, and had a much smaller angle than 26 degrees. To give you some perspective, again, let's pull out our old protractor and look at what 26 degrees would be. 26 degrees below horizontal. Actually, I should do it below so it makes a little bit more sense. So that would be roughly going right through the center of that. I got to go right to here. So that's a pretty big sag, that angle right there. Actually, there you go. So that's the 26 degree roughly. So that gives you an idea of how much of a sag that would be. It might also be neat to find out at what V you have to go to make the angle 5 degrees. So let's say example. What must V be to make theta equal to 5 degrees and then 1 degree? Okay. So in this case, we're going to say, well, I know V squared is equal to GR over tangent theta. So V squared is equal to GR over tangent theta. So I can go ahead and type, put all this in, 9.80 meters per second times 0.300 meters divided by a tangent of 5 degrees, and then take the square root of all that junk. Notice I had, by writing that, I actually had a equal symbol. That was wrong. This is what I mean about stringing equals along. I don't want you to ever do something like that and have an equal, because this can't be equal to that. So what I'm going to do now is I'm going to say that's equal to V, and now I'll do the calculation. So 9.8 times 0.3 divided by tangent, make sure you're in degree mode, 5. I got 33.604 is what I'm going to take the square root of. So I'll write that square root 33.604, and that's meters squared per second squared. And that gives me 5.79. Actually, might as well call it 5.796. Notice this again, 3 sig figs, and that's meters per second. So that's quite a bit over 10 miles per hour, because we got earlier when we did that problem, we got 2.42 meters per second was equal to 5.41 miles per hour. So that was less than half of 5. So we're more than 10 miles per hour at that point. If we wanted it to be, let's go ahead and do that, by the way. So V at 5 degrees is equal to 5.7, let's call it 80 meters per second to the proper number of sig figs, which equals, again, converting to miles per hour, just quick and easy because I have a calculator to do it. So 5.8, if the decimal button works. This turns out to be 12.97, or about 13 meters per second. Or excuse me, miles per hour. So it's getting a little faster, right? Now let's do part B, which I didn't label them A and B, but obviously it's the second part. So in this case, V is going to equal the square root of GR over tangent theta again. So I can actually string the equals together, and I'm going to do 9.80 meters per second times 0.300 meters over, in this case, it's going to be a tangent of 1 degree. So really all I have to do is take this answer, the 5.80, and multiply it by the square root of tangent 5 over tangent 1. So that works as well. So I'm going to say times square root parentheses tangent 5 divided by tangent 1. And that gives me, holy crap, 12.978 meters per second, which is on the order of, imagine you're already up to as many miles per hour, meters per second, as we had miles per hour on the last one. So 12.98, and I'm going to write that as meters per second, and I'm going to round that to, or convert that to miles per hour. That's 29 miles per hour, 29.0. Okay. So at 5 degrees, we had to move 13 miles per hour. At 1 degree, we had to move almost 30 miles per hour. At 2.42 degrees, we got 26 degrees. So you can see, as you get the angle smaller and smaller, you're going to get a lot faster. And that's because that inverse tangent function is acting on you. And of course, the inverse tangent goes to 0 as theta goes to 0. So you're actually going to get infinity. Now what we can do is try to figure out. Yeah, some people are saying this is blurry, so let me bring it up close again to you guys. So that's the calculation that I got for the ball swinging over your head. And then the follow-up examples, I used that velocity that we found when we tried to make the bucket go vertically without spilling. And then I found what speed would be required for 5 degrees, and then what speed would be required for 1 degree. And that was 29.0 miles per hour. Sorry about it being blurry, everybody. The internet connection is questionable at best. Hopefully this video will be posted really soon. The other thing we could do with this one is, notice now that we have a valid value for theta, we could actually go back and solve for t now. So for instance, we know, I'm going to do this as example 9. What is T, the tension. So that's our example 9 question. Well, we know that tangent theta turned out to be equal to GR over V squared. So you could imagine, for instance, a triangle that has opposite over adjacent. GR is the opposite. V squared is the adjacent. And then this would be the square root of V squared plus GR. Okay. And this would be the angle theta. So when I look at equation 1, say, now let's look at equation 2. So equation 2 gives us that T times the sine of theta. Sine would be opposite over hypotenuse. So that'd be GR over the square root V squared plus GR. So that's T sine theta is equal to mg. So now you can see the G's cancel out. So in this case, it turns out, actually it doesn't. It just cancels out here. There's still a G in there. So I can't make the statement I was about to use. So now I've got that T will actually equal m square root V squared plus GR over R. And that's our actual tension. So we've solved yet another problem. And that's about it. Time's up. So if you guys got to get split, you're free to go. If you have any questions, you can wait around. We do have I have a lab today, this afternoon. Of course, some of you might be in it. So I will see those of you there at that time, and I will post this as soon as I can.
Your Friday lab, where do you want us to post our error propagation assignment?
Okay, I will make a link down there for that. I thought I already did, but I must not have, or I might not have published it. I'll make it on that week for the lab. So right where the documents are in week, what is it, week 4, I think. Down at the bottom, there'll be a error propagation lab turn-in thing like normal. So you just turn it in as a PDF. You can download it as a Word document, type it in, print it out if you want to, but I wouldn't recommend that. I'd just maybe take photographs and insert them into the Word document where you do the work.
Thanks.
No problem.
I had something that I wanted to share with concerning test questions.
Go for it.
One of the test questions says, for a projectile launched horizontally, the vertical component of its velocity is blank. And I was just kind of wondering about the wording on that, because it says the vertical component of its velocity. So velocity would mean that it would, like, it has a direction. It's not
Right.
just speed.
Right.
And I would think that you would need a frame of reference, or like a definition for what's up and what's down.
So the main thing is it use the appropriate words. Any vector has no component perpendicular to itself. So they said the velocity fired horizontally, that's one direction.
Yeah. Mm-hmm.
And they asked you for the vertical component, that's another direction. Those two directions are perpendicular to each other. So I think you can tell what the answer should be, right?
That is not the correct answer according to the key.
Oh, really?
Yes.
I will check that and you'll get credit for it. Thanks for letting me know.
No, I got the question correct because I ran into the same question in the practice test.
Okay, well, that means I gotta correct it 2 places then. But yeah, I'll correct it, and you won't get points taken off for putting what you learned from the practice test. I'll make sure that's the case. But just do learn that 0 is the right answer.
Gotcha. Well, and so it says projectile, which I took to imply that this is something being fired in a real world scenario, so that gravity was a factor in this. But yeah, it was a bit confusing. The wording is a bit vague on
Yeah,
that one.
that's part of the problem when you make up a multiple choice problem for physics, because you either got to draw the coordinate system for them so that they give you exactly the right answer, or they got to use words that mean something very specific, but they're not necessarily the words that you're used to. You know, horizontal and vertical is not readily thought of in terms of X, Y, Z and components and stuff like that, but it, you know, it's still correct. So yeah, the wording is a problem that you sort of need to learn, but I wouldn't worry too much about not knowing it this time. Just now keep that as a mental note that horizontal definitely means left and right, vertical definitely means up and down. And if you talk about something pointing one of those directions, it can't have any component pointing the other direction.
Yeah, like if it was moving in that direction, I would have understood that a vertical component would be 0 because it is moving horizontally. But it said that it was launched, so I figured that gravity would be there.
Yeah, yeah. So they literally mean the instant it came out of the barrel, or whatever, you know, shot it. So yeah, it's supposed to be 0. But anyways, yeah, I'll address that and check it out with the key. And now I got to track down where it came from. So at least it's only chapters 3 and 4.
That was for test 2. Yes. I also had another one that I wanted you to look at. Could I share screen for this one?
Yeah, let me make it possible so you can do that. Okay, you should be able to now.
Okay, so this one.
2 objects push on each other. First object has a mass of 30.0 kilograms and accelerates 2 meters per second. The second object has a mass of 7 kilograms if no other forces are acting. Okay, so really what you see here is the force on the first object is the opposite of the first force on the second object. So if you can figure out the force from the 30 kilogram, 2 meters per second every second, which is obviously 60 newtons, then you know the force on the 7 kilogram object would also be 60 newtons, but in the opposite direction. So the first object was
put in the opposite direction.
Yeah. So
first, and so it's not saying the like what is the force? It's saying what is the acceleration of the second object?
Exactly. And obviously the first object was accelerated to the east, so the other one's going to have to be accelerated to the west.
Well, so it says that it is accelerating. So that means that a force is consistently acting on the object, correct?
Well, if it's accelerating or it accelerated, then that just meant a net force that was not 0 happened at some instant. And as soon as that force is removed, yes, it stops accelerating and goes whatever speed it reached. But they're talking about why it's still contacting, basically.
Well, I mean,
you're thinking about the right
like
things, but you're making it harder on yourself. So
I was really confused about this because it was saying that they push on each other,
right?
And so is it basically saying? See, it says 2 objects push on each other. That was the bit that was messing with me. I was under the impression that the first object was pushing on the second object and they were both moving in the same direction.
No, not at all. Yeah. So what this is more like is a child ice skater.
Because what I did was I combined the masses of the 2 objects, because in my mind what I saw was that a 30 kilogram object is accelerating 2 meters per second squared in the easterly direction, and then it collides with the second object. And if the same force is acting on that now combined mass, what is the new acceleration? That was the way I imagined it in my head.
Yeah, that's not the way it was meant. It just says 2 objects push on each other. What that means is you can imagine like I said, a kid on ice skates and a ball on ice skates, or something on a frictionless surface is the main thing. And maybe it's a puppy down there. So the kid pushes the puppy, and accelerates at 2 meters per second. So the kid pushes the puppy, and because the kid pushed the puppy, the kid accelerates away while still pushing on the puppy at a rate of 2 meters per second every second. Well, that means the puppy is applying the force that made that kid move at 2 meters per second. And of course, Newton's third law suggests that that puppy experiences the exact same magnitude force, but in the opposite direction. And therefore, once you get the Newtons being 60, then you have 60 Newtons is equal to 7 kilograms times A. And you'll see that it's west. And if you divide 60 by 7, 7 goes into what? 7 times would be 49, 8 times would be 56. So 8 and 4. 6,
So it's the 8.57 then.
Yeah, 8.57 meters per second west.
Okay.
Yeah.
Yeah.
Yeah,
no,
you
this
just
this
misread
one
that
kind
one.
of confused me because the wording on it was different.
Yeah, I don't see how they could have worded it differently, but yeah, something. Man, I'm not easily coming up. You could put a lot more sentences on it. You could say, it would be better if you
say
said a
two
puppy and a
objects
person
push
face
away
each
from
other.
each other.
Yeah, away from each other would be a little nicer, a lot nicer actually. That would make more sense for you. But yeah, that's how that's supposed to be done.
Gotcha. Okay.
All right.
That was all I was wondering about. I think that was a test question anyways. I run through a couple of the practice tests until I consistently get a high score before I do the real ones.
Yeah, exactly.
Just to make sure I'm familiar with what's going on.
Yeah, that's the best way, and that'd keep you, like in the case that we thought earlier about the zero. That allowed you to get the right answer for the test, even though it was physically wrong. That shouldn't happen. I should never, reward someone for getting the wrong answer. But I just wanted to tell you it was wrong, and you seem to have figured that out anyway. So that's good.
Yeah, that one was strange. It's what was it? It said for a projectile launched horizontally, the vertical component of its velocity, and the correct answer was increases. So it's accelerating upward into the sky is what it was implying, and that was the correct answer. I was like, okay. Whatever.
So it didn't have numbers as answers. It had.
Yeah, it had increases, decreases, stays constant, is 0 for the options.
Okay, gotcha. So yeah, in reality, that question is right as it's written. So that's not an error, because those are the answer choices. What they're trying to get you to figure out is that basically for projectiles, they have a constant acceleration vertically.
Well, so they do have a constant acceleration vertically, but it says the component of its velocity. So wouldn't it be continuously decreases since it is accelerating downward?
No, not necessarily. Remember,
because speed would be increasing because the magnitude is increasing, but velocity is going in the negative direction.
There's a problem. Yeah, and they should have been a little more careful. I'll look at that question anyways. You're going to get full credit because you chose the right one according to the key anyways. But I will look at that. That might be something I have to massage a little bit, because if they ask you for the velocity is increasing or decreasing, I want people to think of speed as the magnitude. So you might say the speed is increasing or decreasing. That would be a better thing than say the velocity is increasing or decreasing. So I might have to change that, and that would make more sense. But yeah, increasing is what it is actually doing. The vertical component actually increases in magnitude. No matter whether it's negative or not, it increases in magnitude.
Yeah. Okay. That's all I was looking for. Thanks.
All right. Have a good one.
See you in an hour, I guess.
See you then.